Imagine a world where information travels not just at the speed of light, but through the strange and mysterious realm of quantum entanglement. A place where hacking is virtually impossible, and communication itself enters a new dimension. Welcome to the quantum internet, the next leap in connectivity that could redefine how we share, store, and protect information. Today on SynapTech, we're exploring the science, the promise, and the challenges of building a global quantum network that might one day revolutionize the internet as we know it. Let's begin with the basics. What exactly is the quantum internet? Unlike the classical internet that relies on electrical or optical signals to send bits of information, ones and zeros, a quantum internet uses the principles of quantum mechanics to transmit qubits. Qubits are unique because they can exist in a superposition of both 0 and 1 at the same time. And thanks to quantum entanglement, they can be instantaneously linked to one another, no matter how far apart they are. So, why does this matter? For one, quantum entanglement makes eavesdropping virtually impossible. Any attempt to intercept a quantum signal collapses its state, alerting both sender and receiver to the intrusion. This means the quantum internet could offer unbreakable security, a dream come true in an age of constant cyber threats and data breaches. But let's unpack how this works in practice. Quantum key distribution, or QKD, is one of the most promising technologies in this field. QKD allows two parties to share an encryption key using quantum properties like entanglement or photon polarization. If anyone tries to intercept the key during transmission, the quantum state collapses, immediately signaling a breach. This makes QKD an incredibly powerful tool for securing financial transactions, government communications, and sensitive personal data. Of course, building a quantum internet isn't as simple as flipping a switch. Unlike classical signals that can be amplified and routed over long distances, quantum information is fragile. It's highly susceptible to loss and noise and can't be cloned or copied. This is where quantum repeaters come in, special devices that extend the range of quantum signals by entangling them with other particles along the way, effectively bridging vast distances. So, how far along are we? Right now, several countries and research institutions are racing to build the first working prototypes of a quantum internet. China has made significant strides with its Micius satellite, demonstrating quantum key distribution between Beijing and Vienna. Meanwhile, Europe is investing heavily in the Quantum Communication Infrastructure project, aiming to create a secure quantum backbone across the continent. In the United States, research labs are working on the Quantum Internet Alliance to integrate quantum communication into existing networks. The potential applications go far beyond security. Imagine connecting quantum computers around the world, sharing entangled qubits to create distributed quantum computing networks that dwarf the power of today's supercomputers. This could revolutionize drug discovery, climate modeling, and AI by solving problems that would take classical computers centuries to crack. But let's not overlook the challenges. Quantum signals are incredibly delicate, requiring near-perfect conditions to maintain entanglement. Even tiny amounts of noise from the environment can collapse the quantum state, destroying the information. Building reliable quantum networks will require advances in materials, science, error correction, and quantum engineering. And then there's the question of integration. How do we connect the quantum internet with our existing classical internet? Researchers are developing hybrid protocols that allow quantum devices to interface with the traditional networks, enabling seamless communication between quantum and classical systems. This will be essential to bringing quantum technology into the mainstream. Of course, no discussion of the quantum internet would be complete without addressing the ethical and security implications. While quantum communication promises unprecedented security, it could also render today's encryption methods obsolete. Nations that lead in quantum technology might gain significant strategic advantages, reshaping the global balance of power. This raises questions about international cooperation, regulation, and ensuring that quantum technology benefits all of humanity, not just a select few. As we move closer to a world where the quantum internet becomes a reality, we must also consider its impact on our daily lives. Will every device be quantum-enabled, from smartphones to smart homes? How will businesses, governments, and individuals adapt to this new paradigm? And perhaps most importantly, how do we ensure that this technology is developed and deployed responsibly, with safeguards to protect privacy, security, and human rights? The future of the quantum internet is both thrilling and uncertain. It promises to revolutionize communication, computing, and cybersecurity, but it also challenges us to think deeply about how we shape the technologies that shape us. At Synaptech, we believe that understanding these innovations is the first step toward building a better, more connected, and more secure world. If you found this journey into the quantum internet insightful, be sure to hit that like button, subscribe to Synaptech, and ring the bell icon so you never miss our deep dives into the world of AI and technology. Drop your thoughts in the comments. Do you think the quantum internet will change the world for the better? Stay curious, stay informed, and stay ahead of the curve with Synaptech.